All right, good afternoon, everyone. We're going to go ahead and start off with section 2 of our gases, liquids, and solids unit. And again, we want to start off with what are our objectives for this unit? What are the things that we want to learn by the end? As you start to notice, some of these are actually going to be fairly quick, where others will be a little bit longer. But these are the main concepts that you will need to know and understand. One, to be able to explain the relationship between state of matter and the kinetic energy of the particles. 2, explain how the properties of solids are determined. 3, differentiate between the 3 types of unit cells for crystals. And 4, be able to define and apply the following terms given to you there in the list. I want you to go ahead and take a few moments and rate yourself on this. Do you already understand this? Maybe you've experienced this either through outside camp involvement or other classes that you have taken, or do you know some of it, or are you completely lost? This is all brand new information to you. Now, we're going to go ahead and get started. And the first thing that we want to talk about are, what are the properties going to be that determine how a liquid will function? And one of the main things that we'll always go back to within this unit is we're going to look at those intermolecular forces. Depending on how strong those forces are, will tell us a lot about how the boiling point will be, the vapor pressure, as well as the evaporation rate for any given liquid. So just keep in mind, again, the attractions and repulsions among the particles. This is what's going to help to define the concepts and the properties that we need to pay attention to. Now, in terms of evaporation means the point at which the molecules have absorbed enough energy, kinetic energy. They then have the ability to actually escape the surface of the liquid. Many times we'll refer to this instead of vaporization. Evaporation usually means that there's some sort of heat that's been applied. Because there's some heat applied, the molecules tend to move a little bit faster, whereas vaporization, it may be a long process. Now, vapor pressure and boiling point. Vapor pressure is going to be the measure of the force exerted by the gas above the liquid. So at the same time as we have something in a liquid phase, we also have the gas phase that's above it, those molecules that have enough energy that have made it into the gaseous form. Now, while that's happening, they're also bumping back into the liquid. This is what's going to cause our vapor pressure. When we have a solution that has a very, very low threshold for vapor pressure, or will vaporize very easily, we call it volatile. Those are usually going to be the things that will catch on fire or be easily used to explode, whereas things with a very, very high vapor pressure or take a lot of energy to get those molecules moving will tend to not burn or be as spontaneous in our reaction. Now, eventually we'll end up with an equilibrium between these two phases, the gases as well as the liquid. And this is really what we call our vapor pressure. If we increase the temperature, we're also going to increase our vapor pressure, the amount those molecules are moving back and forth. Now, boiling occurs when the molecules in a liquid have enough kinetic energy to vaporize. So when we put a pot of water on the stove, it's not until the pressure outside of the pot and the pressure of the molecules that are coming up out of the water reach the same point that will actually have the water begin to boil or bubble as we would normally think of it. Now, if we have a higher pressure outside, that means we're also going to have a higher boiling point. But if we have a low pressure outside, that's going to lower our boiling point. To give you an example, in a normal situation, if we said at sea level, we wouldn't be able to boil water at 70 degrees Celsius. But if we're at a much lower pressure, that means the vapor pressure does not have to equalize out as much as given to us in our example here to the right. If we look at this value, you notice that we have 34 kilopascals of pressure. This is our clue that we have a much, much lower vapor pressure, and therefore we will have a lower boiling point. Whereas now, if we're dealing with a regular situation, or normal, what we would call it, 101.3 kilopascals, we're going to have a vapor pressure that is closer to 100 degrees Celsius. Now, of course, all the time this will not be exact, but this is the relationship that we're going to be utilizing as we go throughout this unit. Now, transitioning away from liquids, we want to take a little bit of time and look at the structures of solids. And these are kind of I'll say the fun parts at times. We want to see how are the structure and properties of solids related. Now, the main properties that we look at in a solid are going to be reflected by the arrangement of their particles and fixed locations, and the fixed locations of their particles, When we talked about the state of matter, talking about solids, we said that the molecules or the particles are very, very tightly packed together, that they are going to vibrate back and forth in place. The more energy or the more heat that you add, the more those molecules bump into each other, the further and further that they'll push. But they still many times will remain solid for a certain period of time. When we reach the point at which the solid then changes to a liquid, this is called our melting point. So we had boiling point before as when they change from basically a liquid to a gas, melting point again from solid to liquid. Again, we're trying to overcome those forces that are actually holding the molecules in place or the particles in place. Now, freezing point, of course, if melting point is where it changes from solid to liquid, freezing point would then be where it changes from a liquid back to a solid. With the structure of solids, we're actually going to run into crystals. And many times we think of crystals and we look at diamonds and all these precious stones, but how do we actually form them? How is their structure sort of set up? And so what we're going to use is, many times they'll form crystals of their own or crystalline shape. This is going to be a crystal having sides or faces that intersect at different angles. There are 3 different crystal shapes or unit cells that we're going to utilize to understand what's going on with our crystal shape, our crystal formation. The first is going to be simple cubic. As you see from the picture here on the side, that it is just like having a framework with a particle at each corner. They're going to interact and be, of course, a part of the other crystals that are joined to it, but this is going to be the simple or most primitive of them all. The second is going to be body-centered. So we have similar to our primitive particle at each point, but then you also have within the center of the structure, a particle is also placed. It may be of the same or it may be different. Many times you may see this with ionic compounds. And last but not least, we have what's called face-centered. So if body-centered was in the middle of the structure, we can then expect that a face-centered is going to have one on each of the faces of our prism or our cube that we're going to utilize in this example. Based on this and the shapes that they will take, we'll get all sorts of different structures of crystals, different strengths, and different abilities with them. Now, allotropes. This is one that you may have heard before but not even realized it before. This is going to be where we talk about the different structures of atoms, different structures of elements, how they're arranged in their solid form, but they're still made of the same material. So the 3 main ones that we deal with, the example we use most times, will be about carbon, because carbon has 3 very stable allotropes, one being diamond, graphite, and the other one fullerene or Buckminster fullerene. Now, if you look at the structure for each, you notice that the number of connections that they're able to form are slightly different, and even their arrangement within their structures are completely different. Whereas diamond is more of a structural formula where it continues to build on each other. We notice that graphite is more rings that are interconnected. And then even within the different units or different rings, they're then connected very weakly to another layer. This is going to allow graphite to be very soft and to come right off on the page when you write. Whereas fullerene, one that was recently discovered in the past 20 or so years, has more of a ball structure and is actually known because of its strength. if you've ever heard of someone talking about carbon nanotubes being very, very light, but also very, very strong, this is where we're going to utilize the fullerenes. Now, not all solids are crystals or form crystals, and we need to be able to know a little bit about those that do not form crystals. Those are going to be called amorphous solids, and they basically just lack the internal structure to form the crystals like the others. Some examples that we may utilize and use on a regular basis will be plastic, rubber, asphalt, and glass. Glass being one that's very important, and stay tuned for I'm going to post a link for another video where you get a chance to see them blowing glass, because the thing I love about it is when you heat glass up, it doesn't really get to a point where it melts, but it just becomes soft. When it becomes soft, then it becomes pliable, and you can move it around just like you would silly putty. Of course, it's very hot, so you wouldn't touch it with your hands, but you have the ability to then make it into what you want it to be. This is where we're going to end for section 2. Stay tuned. We're going to do section 3 and section 4, and that'll be the information for this unit. Have a great afternoon, and I will see you in class.